The upcoming code snippet brings in various libraries crucial for data analysis and visualization. Let's delve into the role of each import one by aliasing pandas as p. The code makes use of this renowned Python library for manipulating and analyzing data. 2. Renaming the NumPy library as NumPy establishes its fundamental role in scientific computing with Python. 3. The cburn import, renamed Essence, empowers data visualization with its Matplotlib-based tools for crafting appealing statistical graphics. 4. Swapping stats models, API to sim. This Python module enables statistical model estimation, testing, and data exploration. 5. The Matplotlib pplot import, under the guise of Pilt, equips the code with a plotting toolkit for dynamic visualizations in Python. 6. By snagging the OLS ordinary least squares class from statsmodel's formula API, the code gains a handy tool for fitting linear regression models. 7. From the Revolutionizing library, the import of SMODE synthetic minority cover sampling technique offers a solution for rectifying class imbalances in datasets by cover sampling minority classes. 8. Accessing the cheat contingency function from CPI stats enables the performance of chi-square tests to assess the independence of two categorical variables. 9. Importing random undersampler from Revolutionizing provides a technique for tackling class imbalances by undersampling the majority class. Commencing the script with these imports ensures a smooth data analysis and visualization process. Leveraging these libraries collectively can streamline workflows and enrich the analytical output. Each library serves a distinct purpose in managing, analyzing, and presenting data effectively. The presented code snippet showcases how to utilize the Pandas library in Python for accessing a dataset saved in the HACI transport format. Specifically, it pertains to extracting information from a dataset associated with the behavioral risk factor surveillance system bursts. In essence, the code accomplishes the following tasks. 1. It establishes the file path pointing to the KEC file holding the bursts dataset. 2. It leverages the PEAT reads function within the Pandas library to interpret the contents of the KEC file and inject them into a Pandas data frame. This code segment is vital for interacting with data confined in the KEC file structure. With Pandas, one can seamlessly peruse various file types, such as hacked files, and seamlessly transfer them into a data frame for subsequent examination and manipulation within Python. This piece of code extracts specific columns from a data frame labeled bursts and stores them in a fresh data frame named burstcode. The columns of interest include veteran 3, Gentlev, Idua, Kajadi, and Men14. This coding technique proves to be quite handy when dealing with extensive datasets featuring numerous columns, yet your analysis or task revolves around only a handful of them. By isolating and generating a new data frame containing solely the essential columns, you streamline your analysis, cut down on memory consumption, and enhance the efficacy of your code. Broadly speaking, segmenting data frames in this manner enables you to concentrate solely on the pertinent sections of your dataset, ultimately rendering your code more streamlined and manageable. Below is a code snippet that reveals the count of records and attributes present in a dataset labeled burstcode. To begin, the Pandas data frame burstcode leverages the shape attribute to ascertain the dataset's dimensions. The initial element of the shape attribute signifies the quantity of rows or records housed in the dataset, while the subsequent element represents the quantity of columns or attributes noted in the dataset. By showcasing these values, we can promptly grasp the dataset's scale and composition. Such insight proves beneficial for dissecting and studying the data to gauge its breadth and intricacy. This particular piece of code seems to play a crucial role in a data analysis or data processing routine. Let's delve into the breakdown. 1. Numericolons burstcode. Select absolute float initially. This command filters out solely the columns from the data frame burstcode that hold numeric values like integers or floats. 2. Missing numvalues numericolons. Isna. Sum following that. This step pinpoints any absent non-data entries within the designated numeric columns. The function JISNA in Pandas data frame generates a Boolean data frame signifying whether each item is non or not. Subsequently, sum tallies the frequency of missing values in each column. 3. Lastly, missing numvalues exhibits the compiled count of absent values within each numeric column. Such a code segment proves highly beneficial in pinpointing and managing missing data within numeric columns, an essential phase in data scrutiny and machine learning undertakings. By grasping the quantity of absent values present across every numeric column, data analysts can then craft appropriate solutions like imputation or the discarding of cross-clones. The following piece of code deals with missing data in a Pandas data frame called burstcode by substituting them with the median values of specific columns better entries. Gentlev, Idua. Here's a breakdown of what the code accomplishes and the rationale behind its implementation. Firstly, the code computes the median for each of the columns veteran entries. Gentlev and Idua. These median values are then recorded in a dictionary labeled as median dit, where the column name service keys paired with their corresponding medians. Subsequently, the fill-in function is invoked on the data frame birthstone to swap out missing values in the indicated columns with the respective median figures. By setting in place true, the adjustments are applied directly to birthstone. Following the data imputation, the code determines the count of missing values in the columns vector entries, genmulf, and idua, storing this information in missing number list after imputation. Lastly, it displays the missing number list after imputation, offering insight into the number of missing values that were substituted with median values. The act of substituting missing values with the median or mean is a prevalent method in data processing for handling absent data points in a dataset. This practice aids in upholding the dataset's integrity and facilitates unbiased analysis by addressing missing values. It proves particularly beneficial when managing numerical data, where the median stands out as a robust measure of central tendency impervious to outliers. The following script serves to compute the source for the information stored in the birthstone data frame with the intent of pinpointing any outliers. Initially, it derives the source through the computation of the absolute difference between each datum and the mean of the corresponding column, which is then divided by the standard deviation of that column. Next, a benchmark of 3 is set for the source, designating any source surpassing this value as an outliar. Subsequently, the algorithm detects outliers by examining whether any source within a row exceed the established threshold of 3. Ultimately, the script displays the rows from the data frame birthstone that contain outliers, signified by the computed source. Such a piece of code proves valuable for preparing data and detecting anomalies during statistical evaluations. The discernment of outliers aids in data refinement, enhances the precision of statistical interpretations, and mitigates the risk of misguiding conclusions. Handling outliers correctly in data analysis is vital for ensuring the durability and dependability of the insights derived from the data. The given code carries out a series of operations. Initially, it computes descriptive statistics for the birthstone dataset using the described function with specified percentiles. Next, it determines the mode of the birthstone dataset by utilizing the mode function, extracting the first value if multiple modes exist with a closed row. The code then transforms the data frame of descriptive statistics by transposing it, switching statistic types to rows and variables to columns. A new row is appended in the transposed data frame for the calculated mode value. Subsequently, the code displays the updated descriptive statistics data frame, now inclusive of the mode. This code is essential for assessing the data's central tendency and distribution in birthstone. Descriptive statistics such as mean, median, quartiles, and mode offer valuable insights into the data's attributes, aiding in comprehending its distribution, central tendency, variability, and prevalent values. This examination plays a pivotal role in summarizing the dataset, identifying patterns, anomalies, and guiding subsequent data analysis and decision-making processes. This snippet of code serves the purpose of displaying distinct values identified within a designated column vector entry of a dataset referred to as birthstones. In Python, the unique function is utilized as a tool to extract a roster of singular elements from a designated entity. Employing this code can prove beneficial in delving into the discrete values existing within a specified dataset column, facilitating a deeper comprehension of the diverse classifications or tiers within that column. Such exploration can play a crucial role in tasks such as data analysis, data refinement, and gaining a comprehensive overview of the dataset's organization. The following script utilizes the matplotlib pplot package in Python to create a histogram plot. Specifically, it generates a histogram based on the information stored in the vector entry column of the birthstone dataset. The code functions as follows. 1. By executing splt, hist birthstone vector entry, bins named color steel blue, edge color black. A histogram is formed using the dataset values from the vector entry column. It dictates the presence of 9 bins, assigns a steel blue hue to the bars, and outlines the bars in black. 2. The line splt Klebel vector entry designates the x-axis label as vector entries, representing the plotted variable. 3. Setting the y-axis label as frequency is achieved with splt label frequency, indicating the count of data points within each bin. 4. Upplt title histogram of vector entry variable assigns the plot's title as histogram of vector entry variable. 5. To exhibit the histogram plot, splt show is utilized. Histograms are beneficial for visualizing dataset distributions. Each bar's height reflects the data frequency within a specific range, aiding in the prompt identification of patterns, outliers, and overall data distribution shape. Employing this code is vital as visualizing data through plots like histograms provides valuable insights into data distribution, aiding in data exploration, comprehending data traits, and facilitating informed decision-making throughout data analysis. The following code snippet carries out filtering on the vector entry column within the birthstone data frame. It excludes rows containing values of 7 or 9 and subsequently displays the distinct values present in the vector entry column post-filtering. This piece of code plays a vital role in data preparation and refinement. It targets specific values in the veteran entry column that could skew the analysis or lead to inaccuracies. Through the removal of such rows, the integrity and applicability of the dataset for analysis are substantially enhanced. This script extracts data from a data frame named birthstone by selecting the veteran entry column, assumed to denote veteran status with values 1 for yes and 2 for no. Subsequently, it generates a new column labeled veteran within the same data frame. The script updates values from 1 to yes and from 2 to no. Following this transformation, the script displays the distinct categories present in the veteran column, signifying the refined representation of veteran status as yes and no. Such code proves valuable for initial data manipulations, particularly when converting encoded categorical data, such as 1s and 2s, into more descriptive textual labels like yes and no. This conversion enhances data comprehension and facilitates subsequent analysis. Printing the unique values serves the dual purpose of confirming the successful substitution and providing insights into the composition of entries within the veteran column. Utilizing the matplotlib library in Python, this script creates a histogram that showcases the distribution of the veteran variable from the birthstone data frame. The histogram consists of 9 bins, shaded in a steel blue hue with a sleek black outline. On the graph, the x-axis pertains to the veteran variable, while the y-axis displays the frequency for each bin. The title of the histogram is tagged as histogram of veteran variable. Histograms serve as valuable tools for grasping the spread of numerical data, pinpointing trends, or detecting any anomalies within the dataset. They offer a visual insight into the data distribution, aiding in informed decision-making processes. In this context, the histogram plays a vital role in visualizing the distribution of responses associated with the veteran variable present in the dataset. The provided code isolates the distinct values found in the genelf column within the birthstone dataset and displays them in the console. Through the application of the unique function, duplicate entries are disregarded, presenting solely the exclusive values within the designated column. Recognizing the unique entries within a particular column proves beneficial in data examination, facilitating the comprehension of data distribution and the detection of probable anomalies like absent or erroneous values. This code segment serves as a valuable asset for embarking on data exploration and fundamental data profiling duties. The following script creates a histogram based on the data found in the genelf column of the birthstone dataset. The histogram is designed to feature 9 bins and will be colored in a shade resembling steel blue, accentuated by black edges for a visually appealing display. Histograms offer a graphical illustration showcasing the distribution frequency of the genelf attribute in the dataset. They allow us to visualize how the genelf values are dispersed among different categories and their respective occurrence frequencies. By utilizing the clabel function to assign the x-axis label as genelf, the ilabel function to designate the y-axis label as frequency, and the title function to establish the histogram title as histogram of genelf variable, we enhance the clarity and context of the histogram visualization. The presentation of this histogram enhances comprehension of data distribution, serving as a valuable asset for exploratory data analysis by facilitating the detection of trends or anomalies within the dataset. The provided script filters out rows from a data frame called birthstone based on the genelf column values. It specifically targets rows with genelf values of 1, 3, or 5. Subsequently, it displays the distinct values found in the genelf column of this refined data frame. This script serves the purpose of honing in on particular data subsets that match specific criteria, such as isolating data associated with particular health states denoted by the values 1, 3, and 5 in the genelf column. This segmentation streamlines the capacity for in-depth scrutiny or manipulation solely concerning this subset of information, facilitating the extraction of insights or conclusions pertinent to these distinct health conditions. The provided code snippet serves a few key purposes. 1. It establishes a dictionary named category mapping that links numeric values 1, 3, 5 to specific health categories: excellent, good, poor. 2. Within the birthstone data frame, it swaps the values in the genelf column with their corresponding health category counterparts using the replace method and the category mapping dictionary. The altered data is then stored in a fresh column labeled general health. 3. Following this process, the code generates a display of the distinct values found in the general health column. Employing this code snippet proves beneficial when dealing with numerical categories in a dataset, facilitating the transformation into meaningful categorical values for enhanced comprehension and analysis. By refining the data in this manner, it streamlines the data's interpretation, rendering it more accessible and easily understandable. Specifically, in this instance, it assists in converting numerical health assessments into their respective health categories. This snippet of code is handy for creating a histogram that displays the distribution of values within the general health variable found in a dataset named birthstones. By utilizing the pult hist function, the histogram is generated with predefined specifications, such as dividing the data into 9 bins. The color scheme chosen for the bars is steel blue complemented by black edges. To enhance the visualization, the subsequent commands assign labels to the X and Y axis general health and frequency, respectively, and provide a title for the plot histogram of general health variable. To view the histogram, the plot show function is employed. This code proves valuable for visually analyzing the distribution of the general health variable within the dataset, offering insights into the range and density of values. Histograms are widely used to visually represent the frequency or volume of data within specific ranges or segments. Below is a snazzy piece of code that comes in handy for printing out the distinct values found in the EDUA column from a dataset that goes by the name birthstones. The aim here is to fish out and showcase all the one-of-a-kind educational attainment levels that pop up in the EDUA column. This code serves as a nifty tool for delving into the data and wrapping your head around how the information is spread out in a particular column. It works wonders for pinpointing the exclusive categories nestled within a categorical column, such as educational levels in this scenario. By trotting out these unique values, we lay eyes on the breadth and distribution of educational levels housed in the dataset. Grasping these distinctive values proves crucial when it's time to spruce up and propose the data, as it lets us catch any hiccups or hitches hanging out in the dataset. This intel also steers us in deciding how to go about managing different categories when it comes to analysis or modeling. This script generates a histogram representing the EDUA variable from the dataset birthstone. Divided into 9 bins with the bin's 9 parameter, the histogram features bars colored in steel blue with black edges to enhance visibility. Set using the color steel blue and edge color black parameters, the x-axis denotes EDUA, the y-axis represents frequency, and the plot is titled histogram of EDUA variable, designated by pilt, clibel, pilt, xylabel, and pilt, title functions respectively. Histograms offer a visual insight into the spread of a continuous variable. Analyzing the EDUA variable's distribution aids in recognizing any data patterns or outliers. By customizing colors, labels, and titles, the plot elevates its informativeness, making data interpretation more straightforward. The provided code excerpt filters a data frame labeled birthstone by exclusively picking the rows where the values in the column EDUA fall within the range of 2 to 6. Subsequently, it displays the distinct values found in the EDUA column of the refined data frame. This type of code serves the purpose of tidying up and organizing data by singling out a subset of records conforming to specified conditions. Filtering data plays a pivotal role in data scrutiny, enabling a focus on pertinent details while omitting any inconsequential or abnormal data entries. The intent here is to ensure that solely the data featuring EDUA values ranging from 2 through 6 undergoes further examination. This script is essentially converting numerical education levels into specific categories and then updating the existing education column in a data frame with these categories. Here's a breakdown of the script's functionality. 1. It initializes a dictionary named EDUMapping where numerical values correspond to different education levels, mapping them to their respective categories. 2. By utilizing the replace method with the EDUMapping dictionary, it substitutes the EDUA column values in the birthstone data frame with the appropriate education categories. 3. The EDUA column is then eliminated from the birthstone data frame utilizing the drop method within playatruth. 4. Finally, the script prints out the distinct values found in the education column of the birthstone data frame. This code serves the purpose of converting numeric education values into more understandable categories, facilitating data comprehension and analysis. Additionally, it plays a crucial role in standardizing and refining the data for future analytical tasks or visual representation. The snippet of code below generates a histogram illustrating the distribution of the education variable extracted from the birthstone dataset. By specifying 9 bins, the histogram is segmented into different sections. The bars of the histogram are shaded in a cool steel blue hue, accentuated with a sharp black outline using the color and edge color parameters. The x-axis is appropriately labeled as education, while the y-axis is designated as frequency. The plot is entitled Histogram of Education Variable, delivering a visual depiction of the diverse educational levels found in the dataset. Employing this code proves paramount in visually interpreting the distribution of the education variable, offering valuable insights into the prevalence of various educational backgrounds within the dataset. This visual aid enriches the comprehension of underlying patterns, trends, and correlations present in the data. The provided code snippet is designed to display the distinct values found in the KGED column of the dataset birthstone. It generates a list showcasing the unique values occurring in that specific column. Such a code snippet proves beneficial for exploring and revealing the diverse categories or standalone values existing within a designated dataset column. This practice enhances our comprehension of the data, providing valuable insights into the potential contents of the column. Grasping the categorical data within a column stands as a vital element for a multitude of data-related operations and analytical endeavors. This snippet of code generates a histogram based on the information found in the KGED column of the birthstone dataset. It sets the number of bins to 9 and customizes the bar color to steel blue and the edge color to black. The plot's axis is labeled as Kajiti, the y-axis as frequency, and the title as histogram of Kajiti variable. Histograms are a useful tool for illustrating the spread of a single numerical attribute. They provide a quick overview of the data's central tendencies, variability, and distribution shape. This visualization aids in recognizing data patterns and any potential outliers. The code supplied facilitates the creation of a visual representation that enhances comprehension of the age distribution present in the Kajiti column of the dataset. In this code snippet, individuals in a dataset are segmented into 3 categories based on their age: 18 to 34, 35 to 54, and 55. Initially, it utilizes GLOW to assign the respective age group labels according to the predefined age ranges. With each condition, it verifies if the values in the Kajiti column fall within the specified age brackets 1834, 3554, or 55 and above, and then tags them accordingly under the age group column. Subsequently, it transforms the age group column to a categorical data type by employing as type category. This data type is advantageous for variables with a fixed and distinct set of values, enhancing efficiency and conserving memory. Lastly, it displays the distinct values present in the age group column to ensure the accurate classification. This code proves invaluable for edge-based data analysis and summation, facilitating statistical evaluations and visualizations tailored to each age group. Its utility spans across various fields like public health investigations, marketing assessments, or any scenario necessitating age-based segmentation. The provided script generates a histogram based on the age group column extracted from the Birthstone dataset. It sets up the histogram with 9 bins, sporting a steel blue color and bordered in black. By segmenting the age group values into 9 evenly sized intervals, the code effectively tallies the frequency of data points falling within each interval, portraying this information graphically through the histogram bars. Incorporating axis labels and a descriptive title significantly enhances the interpretability of the histogram. Clarifying the represented data, this script serves as a handy tool for promptly visualizing the distribution characteristics of the age group variable, aiding in the exploration of age distribution trends within the dataset. The following script extracts and outputs the distinct values found in the MEN14 column within the Birthstone data frame. This code snippet serves to showcase the exclusive values existing in the designated column of the data frame. Employing this script enables a rapid examination and comprehension of the diverse categories or responses housed in the particular dataset column. Such an approach proves beneficial for delving into data, ensuring its tidiness, and conducting thorough analysis. This script creates a histogram for the specific variable MEN14 extracted from the dataset Birthstones. The histogram will consist of 9 bins and will be styled in steel blue with black borders. The x-axis will be labeled as MEN14, the y-axis as frequency, and the histogram's title will read histogram of MEN14 variable. Histograms prove valuable in illustrating the distribution of a solitary variable, showcasing the frequency or tally of diverse values within the variable. They aid in spotting patterns like skewness, peaks, or gaps in the data. This script plays a pivotal role in exploring and analyzing data by enhancing our comprehension of the distribution of the focal variable. The provided code snippet deals with processing mental health data extracted from the behavioral risk factor surveillance system bursts. To break it down in more casual terms, 1. Initially, the code tweaks the column MEN14 in the Birthstone data frame, changing it into numerical values. Any conversion mishaps are brushed off without causing a disturbance. 2. Subsequently, a nifty lambda function swings into action post the numerical swatheroo. This function crafts a fresh column dubbed mental health in the Birthstone data frame. Its mission: to assign values as follows: scores of 13 or lower get a cozy 0. Scores of 14 or higher earn a snazzy 1. Any other scores are kindly labeled as none. 3. The grand finale involves a peek at the mental health column's distinct gang of values. The sneak peek reveals the neat categories born out of the lambda function's conditions. Essentially, this code jazzes up the MEN14 column, which likely contains numerical responses for mental health surveys, by stamping these responses into more meaningful categories: 0 for 13 or below, 1 for 14 and up. The code streamlines the data for smoother analysis and unlocks the door to deeper statistical dives or clearer visualizations. In this script, mental health data from a dataset is being manipulated for analysis. Initially, the script screens out rows with a specific value in the MEN14 column, excluding those with a value of 9. Next, a mapping dictionary is constructed to merge categories 1 and 2 under a unified category 0 while relabeling category 3 as 1. Subsequently, the mapping is applied to the MEN14 column, introducing the transformed data as a fresh column mental health in the dataset. To conclude, the script displays the distinct values recorded in the mental health column. This code is imperative for refining and converting the dataset, sifting out undesired or inaccurate records, and establishing a new format that can enhance the significance and relevance for subsequent analysis or visualization. The conversion of categories into new values streamlines the data's comprehension and analytical process. The provided script tallies up the frequencies of individual values present in the mental health column of a data frame named birthstones. By utilizing the value counts method in Pandas, a series is generated displaying the count of each distinct value in a descending fashion. This approach proves handy for swiftly grasping the distribution of values in a particular column of a dataset. It aids in pinpointing prevalent themes or tendencies concerning mental health status in this scenario. Such insights hold immense significance for carrying out additional evaluations and shaping well-grounded judgments derived from the dataset. The script below generates a bar chart illustrating the frequency of each category within the mental health column of the dataset named birthstones. The plot size is adjusted to 10x to control its dimensions effectively. To construct the bar chart, the code leverages the countplot function from the Seaborn library, with the x-axis depicting the different mental health groups. Moreover, the plot's title is configured as versus mental health, while the x-axis and y-axis are labeled as mental health status and count, respectively. To prevent label overlap, the x-axis labels are rotated by 45 degrees, ensuring clarity especially for longer labels. To enhance the plot's aesthetics and spacing, the tight layout function is employed to fine-tune the subplot parameters automatically. Finally, the show function displays the plot accordingly. This code snippet proves valuable for visually representing the distribution of categorical data in the mental health column, aiding in prompt analysis and interpretation of mental health status counts through visual cues. This visual approach facilitates the identification of potential patterns or trends embedded within the dataset. This code snippet focuses on tackling the challenge of class imbalance within a mental health dataset. To begin with, the code segment initiates by segregating the dataset into two main components: the features X representing the independent variables and the target Y representing the dependent variable. Here, the mental health column signifies the target variable denoting the mental health condition. Subsequently, the code employs the random undersampler method to rectify the imbalance by deliberately undersampling the overrepresented majority class, which likely pertains to a specific mental health status. Following the resampling process, the code calculates the frequencies of each class within the resampled dataset to assess whether the rebalancing has been effective. Lastly, the code generates a bar plot to visualize the distribution of mental health statuses post-resampling. This graphical representation aids in comprehending the efficacy of the resampling method in balancing out the classes, thereby facilitating a clearer interpretation of the mental health status distribution in the dataset. In essence, this code excerpt serves as a valuable tool for managing skewed datasets, specifically addressing class imbalances within the mental health target variable. This approach ensures enhanced resilience in modeling and prediction accuracy when implementing machine learning algorithms. Handling imbalanced data is crucial in machine learning to prevent bias towards the majority class. The code presented below tackles this issue initially. It merges the features resampled and the target variable U resampled horizontally to form a resampled data frame resampled. Subsequently, it displays the frequency distribution of the mental health column in the resampled data frame to exhibit the target variable's distribution post-resampling. The goal of resampling is to even out the class distribution, offering the model a more balanced training set. This process enhances the model's performance, lessening the likelihood of skewed predictions. The resampling method utilized in this code effectively tackles imbalanced data concerns, potentially resulting in more precise and dependable machine learning models. The following code snippet generates a fresh data frame labeled as burst2, mirroring an existing data frame named resampled. If the duplicated data frame, burst2, retains identical data and column arrangements as the initial data frame, safeguarding the original data from any modifications performed on burst2. This approach is commonly employed when necessitating a working duplicate of a data frame to execute alterations or enhancements without influencing the primary dataset. It proves beneficial when exploring diverse data manipulation or analytical methods, enabling the preservation of an untouched duplicate of the initial dataset for review or contrasting purposes. The given code snippet displays the variable burst2 in Python, revealing its stored value when executed. To delve deeper into the code's full functionality and purpose, examining the definition of burst2 is crucial. The variable's content might vary widely, ranging from a string, number, list, dictionary, or other data types. In isolation, the provided code excerpt lacks adequate context to elucidate its precise operations. It primarily serves the purpose of showcasing the value assigned to burst2. In this snippet of code, columns are removed from a data frame labeled burst2. The columns slated for removal are veteran 3, gentle, kajadi, and meant for teened. By setting in place true, the alterations are made straight to the primary data frame burst2, bypassing the creation of a new data frame. This code is handy when you aim to streamline the data frame by trimming surplus columns. honing in on pertinent data for analysis. Doing so can boost the efficiency of analysis and visualization tasks by excluding extraneous or unimportant columns. The presented script conducts a chi-square test of independence to evaluate the connection between two categorical variables, namely a group and veteran, within a given dataset. Initially, the script tabulates the data by enumerating the occurrences of distinct pairings of a group and veteran classifications. Subsequently, the contingency function sorted from the CIPI library is leveraged to compute essential metrics such as the chi-square statistic, value, degrees of freedom, and anticipated frequencies derived from the contingency table. The outcomes are then exhibited on the screen, offering insights into the potential significant correlation between the group and veteran attributes within the dataset. A chi-square test serves as a valuable statistical tool for assessing potential connections between two categorical variables. Employing this test is crucial for discerning relationships between variables and guiding decisions based on the test outcomes. This code snippet conducts a chi-square test to examine the independence of the categorical variables group and general health within the BRS2 dataset. Here's how it functions. To begin, it constructs a contingency table named Contingent Group General Health using the PID-ROSTAB function. This table displays the frequency distribution of group and general health variable combinations. Subsequently, it computes the chi-square statistic for independence, along with the p-values, degrees of freedom, and expected frequencies, utilizing the contingency function from the SCIP library. Lastly, the code displays the outcomes, featuring the chi-square statistic, p-value, degrees of freedom, and expected frequencies for the group and general health variables within the contingency table. This code proves valuable for investigating the correlation between group and general health variables, determining if they are interlinked or freestanding in the dataset. Through the chi-square test, we can evaluate the presence of a significant relationship between the variables and extract meaningful insights from the findings. In this script, a chi-square test is executed to examine the independence of two categorical variables, namely group and education, by assessing the frequency distribution of their combinations. To kick things off, a contingency table is established using the PD-ROSTAB method to display the occurrence counts for each combination of the two variables. Following that, the contingency function from the CIPI library comes into play to calculate the chi-square statistic, value, degrees of freedom, and expected frequencies based on the previously constructed contingency table. The chi-square test enables us to assess if there's a noteworthy connection between the two categorical variables. The p-value serves as an indicator of the strength of evidence against the null hypothesis, which posits that the variables are independent. A lower p-value hints at the potential rejection of the null hypothesis. Outputting the chi-square statistic, p-value, degrees of freedom, and expected frequencies aids in comprehending the relationship between the variables and drawing meaningful insights from the analysis. This code proves indispensable for statistical analysis when the objective is to ascertain the association between two categorical variables within a dataset. The script provided performs calculations for the chi-square statistic and p-value concerning the correlation between mental health status such as self-reported mental health conditions and veteran status, indicating if someone is a veteran. To achieve this a contingency table is formed by tallying the occurrences of different combinations of mental health and veteran statuses. 2. Next, the chi-square test of independence contingency is utilized on this table to determine if there exists a statistically significant connection between mental health and veteran status. 3. The results displayed include the chi-square statistic measuring the variance between observed and anticipated values, the p-value indicating the likelihood of obtaining observed outcomes by chance, degrees of freedom, and the anticipated frequencies under the null hypothesis of independence. This script aids in scrutinizing whether a link exists between mental health status and veteran status within the dataset. The findings from this examination could unveil insights into probable relationships or distinctions between these two factors, which could hold significance in diverse research or public health scenarios. The following script executes a chi-square test to examine independence between two categorical variables, mental health and group, utilizing data from the BRS2 dataset. Initially, it constructs a contingency table by employing the PD-ROSTAB method to tally the occurrences of each unique pairing of values from the variables. Subsequently, it computes the chi-square statistic, p-value, degrees of freedom, and expected frequencies by leveraging the contingency function sorted from the CIPI stats module. The chi-square test serves the purpose of ascertaining whether a notable connection exists between the two categorical variables. Under the null hypothesis, the variables are deemed independent, whereas the alternative hypothesis posits an association between them. Through displaying the outcomes of the chi-square test, encompassing the chi-square statistic, value, degrees of freedom, and expected frequencies, the code sheds light on the correlation between mental health status and age group within the dataset. This script carries significance as it aids in establishing the presence of a substantial relationship between the two categorical variables, imparting statistical proof to bolster decision-making processes or guide further analysis rooted in this association. The following code snippet is designed to carry out a chi-square test of independence between two categorical variables: mental health and general health. Here's a breakdown of how it operates and why it holds significance. 1. The formation of contingency table. To begin, the code constructs a contingency table using the pandas crossed-up function. This table displays the frequency distribution of value combinations for the two categorical variables. 2. The A-square assessment. Subsequently, it computes the chi-square statistic, p-value, degrees of freedom, and expected frequencies by utilizing the contingency function. The chi-square test aids in ascertaining whether a statistically noteworthy correlation exists between the two categorical variables. 3. Displaying results. Lastly, the code showcases the chi-square statistic, p-value, degrees of freedom, and expected frequencies. These outcomes enable us to gauge whether there is a substantial relationship between mental health and general health. Employing this code is crucial as it enables us to objectively evaluate the connection between two categorical variables, specifically mental health and general health. Through conducting a chi-square test, we can ascertain if there exists a statistically significant correlation between these variables, offering valuable insights for further analysis or decision-making endeavors. The code presented conducts a chi-squared test of independence on the mental health and education variables extracted from the BRST2 dataset. Initially, the PT cross-step function generates a contingency table illustrating the distribution of observations across the various categories of mental health and education. Subsequently, the contingency function computes essential statistical metrics like the chi-squared statistic, value, degrees of freedom, and expected frequencies using the previously constructed contingency table. This test aids in recognizing if there exists a significant connection between the two categorical variables. To culminate, the outcomes of the chi-squared test, such as the chi-square statistic, value, degrees of freedom, and expected frequencies assuming independence of the variables, are displayed. Analyzing the statistical link between mental health status and educational attainment is crucial. By deciphering this connection, valuable insights can be gained to facilitate tailored interventions or strategies aimed at enhancing mental health outcomes across distinct educational strata. The following script showcases the data types associated with each column within the BRST2 data frame. Understanding these data structures is key to grasping Python's interpretation of each column. Variables like integers, floats, strings, and dates play a pivotal role in shaping data manipulation and analysis methods. This knowledge proves vital for tasks like data cleansing, filtering, and accurately applying operations to the dataset. In the provided code snippet, the values within the mental health column of the pandas data frame BRST2 were transformed into numeric data type. This operation leverages the PT numeric function found in the pandas library. Subsequently, the script displays the data types of all columns within the BRST2 data frame by utilizing the dtypes attribute. This conversion process proves crucial when the mental health column encapsulates non-numeric values requiring interpretation as numerical entities for subsequent mathematical computations or analytical processes. By executing this conversion, the data within that specific column is formatted appropriately for effective utilization in calculations or other numerical analyses. This code snippet showcases the utilization of the getDummies function within the pandas library to execute one-hot encoding on specific columns found in a data frame identified as BRST2. One-hot encoding is a fundamental procedure applied to translate categorical variables into a structure compatible with machine learning algorithms, ultimately boosting predictive accuracy. It functions by breaking down a categorical column into numerous binary columns, where each individual column signifies a category and denotes the presence 1 or absence 0 of that specific category in a given row. In this instance, the code explicitly designates the veteran, general health, education, and a group columns within the BRST2 data frame for one-hot encoding. The outcome is retained in a freshly created data frame titled BRST3s. Following the execution of getDummies, the code proceeds to display the data types of the columns present in the freshly created data frame BRST3 using the dtypes attribute. This step proves invaluable in verifying the successful completion of the encoding process, ensuring that the columns are now formatted suitably for subsequent data exploration or machine learning endeavors. This code snippet seems to aim at accessing the columns of a data frame called BRST3 using the columns attribute in pandas. In pandas, the columns attribute of a data frame provides a way to retrieve the column labels in a sequential manner. It comes in handy for promptly examining the available columns within the data frame and for pinpointing particular columns for further analysis or handling. When you display the columns attribute, it reveals the names of all columns within the data frame, offering a clearer insight into the data's arrangement and facilitating the selection of specific columns for data analysis or manipulation. This piece of code is crucial for establishing a statistical formula commonly applied in regression analysis. It specifies a linear regression model in which mental health serves as the response variable, while various categorical predictors, such as veteran with yes or no levels, general health with levels like excellent, good, poor, education including levels such as college, elementary, high school, and age group with ranges like 18 to 34, 35 to 54, 55, factor in. The code enables us to build a linear regression model aimed at comprehending the association between these categorical variables and mental health. By employing the C function, the categorical variables are treated as factors within the regression model, generating dummy variables for each category level. This approach facilitates the inclusion of categorical variables in the regression analysis, where each level is depicted by binary indicators 0 or 1. In essence, this code is fundamental for configuring the regression model and outlining the correlation between the response variable and the predictors in statistical analysis, aiding in the exploration of how these categorical variables might impact mental well-being. The provided script executes an analysis of variance ANOVA utilizing Python stats models library. ANOVA serves as a statistical technique to evaluate variations among average values of different groups within a dataset. Breaking down the script 1, initially, a linear regression model is fitted to the dataset burst 3 through the first line of code, employing ordinary least squares abbreviated as OLS while following the specified formula. 2. Subsequently, the ANOVA function, extracted from the stats model's stats ANOVA module, is utilized to generate an ANOVA table based on the prearranged model. The argument type 2 determines the sum of squares variety for the ANOVA analysis. 3. Upon completion, the ANOVA table content is showcased on the console interface. Running this script enables the retrieval of statistical insights regarding the significance of variables within the regression model and their influence on the response variable. This aids in comprehending the associations amid variables and assists in making informed choices grounded on the analysis outcomes. The following script produces a pair of bar plots based on the outcomes of an ANOVA analysis. Initially, the script omits the residual row from the ANOVA findings since it pertains to residual error, which doesn't play a role in the bar plots. Subsequently, utilizing the cburn library since, the script generates two distinct visualizations. 1. The initial plot exhibits the values for each independent variable on the x-axis, plotted against the corresponding values on the y-axis. This visualization offers insight into the impact of individual variables on the response variable. 2. The subsequent plot illustrates the p-values for each variable on the x-axis and their respective p-values on the y-axis. This graphical representation aids in assessing the significance of each variable's influence. Both visuals are accompanied by suitable titles, labels, and category rotation to enhance readability. Such visual aids are crucial for comprehending ANOVA results and pinpointing variables that wield a notable influence on the response variable in statistical analyses. They offer a more intuitive approach to interpreting statistical outcomes compared to a mere examination of figures within the ANOVA summary. In this script, the correlation matrix is being computed for the dataset labeled BRFS3. This matrix illustrates the correlation coefficients among the various variables in the dataset. Correlation coefficients serve as a gauge of the intensity and direction of a linear connection between two variables. These coefficients span from 1 to 1, where 1 signifies a flawless positive linear relationship, 1 represents a perfect negative linear relationship, and 0 indicates no linear relationship whatsoever. The correlation matrix enables the swift identification of positively correlated, negatively correlated, or unrelated variables. This insight proves valuable in comprehending the interrelationships among dataset variables, offering assistance in subsequent data scrutiny and modeling endeavors. The function provided serves the purpose of computing and exhibiting correlated pairs alongside their correlation coefficients derived from a specified correlation matrix. It accomplishes this task by sequentially comparing each pair of columns within the correlation matrix to ascertain the correlation coefficient between them. The operational process of the code can be outlined as follows. 1. A designated list named correlated pairs is initialized to hold the correlated pairs in addition to their correlation coefficients. 2. The code then proceeds to navigate through the columns of the correlation matrix utilizing nested loops. The external loop ranges from the initial column index to the second to last column index, while the internal loop spans from the ongoing column index plus 1 to the final column index. 3. With each column pair, the code gathers the column names, computes the correlation value between the two columns based on the correlation matrix, and appends a tuple of colon, colto, correvalo to the correlated pairs list. 4. Upon completion, the script showcases the correlated pairs together with their correlation coefficients through formatted strings. This piece of code proves to be valuable in recognizing highly correlated column pairs within a dataset, aiding in tasks like feature selection, dimensionality reduction, and the construction of predictive models. By scrutinizing the correlation among column pairs, one gains deeper insights into the data's relationships and interdependencies, enabling the formulation of informed decisions regarding the management and utilization of these correlated features. This snippet of code showcases a heat map visualization of a correlation matrix. Here's a breakdown of each component of the code and its significance to begin. Plot figure fixes 8 establishes the dimensions of the plot figure as 10 inches wide and 8 inches tall. This sizing specification is key for managing the display size effectively. Next, essence, heat map correlation matrix, cannot true, mapper boo, fint. TOOF generates a heat map utilizing Seaborn's heat map functionality. The correlation matrix represents the dataset under examination, enabling Chanotrue integrates the correlation's numerical values into the heat map. This mapper-boosh parameter dictates the color palette employed for data representation, while TOOF customizes the numerical value format on the heat map to 2 decimal places. Moving on, Tiddly correlation matrix designates the plot's title as correlation matrix. This title furnishes context for the visualization, aiding viewers in grasping the information being depicted. Lastly, showcases the plot following the completion of all configurations. This final step is vital for observing and interpreting the heat map visualization of the correlation matrix. In essence, this code excerpt plays a pivotal role in visualizing relationships between variables within a dataset. By leveraging a heat map, we can readily pinpoint connections among different variables, facilitating data comprehension and informed decision-making based on these correlations. The given script analyzes the relationship between the variable mental health and other attributes within the dataset bursts 3s. Initially, it generates a correlation matrix utilizing the core method, evaluating the linear connections between all variable pairs. Subsequently, it isolates the correlations involving the mental health variable from this matrix, excluding self-correlation, which defaults to 1. Following this, the code arranges the correlation coefficients in descending order based on their absolute values, indicating the strength of the relationships. Lastly, it displays the feature names alongside their correlation coefficients with mental health. This script plays a crucial role in identifying the attributes most significantly correlated with mental health, offering insights into the interrelations among variables in the dataset. By highlighting which features potentially impact mental health the most, it aids in comprehending the dataset's dynamics effectively. The provided code excerpt performs correlation analysis on a dataset, likely associated with the behavioral risk factor surveillance system. Initially, it computes the correlation matrix among the dataset features, focusing on the mental health attribute, and arranges them in descending order based on the magnitude of correlation. Subsequently, it isolates the top 10 features most strongly correlated with mental health from the correlation matrix. This subset is then utilized to generate a heat map, visually representing the correlations between these selected features and mental health. This code snippet plays a critical role in data exploration by unveiling associations between various variables within a dataset. Through the heat map visualization, it becomes effortless to pinpoint which features exhibit the closest ties to mental health, enabling potential insights into their impact. Such analyses significantly aid in decision-making, feature prioritization, and the detection of underlying patterns in the dataset.